I've sent you a list of problems that I'd like to discuss, and I think we should start right away with the first one. I'm not sure if you've gotten the link. I've put it on the Discord. In any case, the first problem I'd like to discuss is the following. So, what this task asks us is the following. So, we want to be able to deduce an integer sequence of length n, but we have we can't actually find it. Basically, it's sort of an interactive problem, but not really. We know that we can query the sum on some interval for every single interval ever for a given cost. It gives us that the cost to find out the sum on some interval is Cij, where C is a matrix. So this is a point in that matrix. Uh, and we need to query multiple times some sums such that by the end we know to deduce the integer sequence B. Uh, yeah, that's it. A trivial solution to this problem would be to ask every single element, like every single sum of spanning from one element to the same element. That is, we just query the sum of one single element, and we do this for every single n element. But because the matrix we are given is basically at random, it might be better to like query the sum of the entire array than query just as before n minus one single elements, and then we can deduce the last element by subtracting all of these from the final sum, for example. So maybe that's another solution. And there may be multiple solutions. There may be a ton of solutions. So you need to find the best way to solve the problem, basically. Uh, did everyone understand the statement of the problem? If so, I think we can discuss this as review 2 more minutes, I think. Okay. Does anyone have any ideas they'd like to discuss with regards to this problem? Right now. Okay. In the spirit of trying to make this as uh, pedagogically valuable as possible, I'll give you a hint. Um, like, let's say that this C of ij was a function, and the problem tells us that there's like an oracle or something. Well, the problem is called oracle, but yeah, that Gustavo can give you a sum from pi to pj for a cost ci of cj. And let's say like we are Gustavo actually, and we can calculate uh, the ci of j is like a polynomial function or whatever. I don't know. But we also have to give this guy Alfredo the sum from I to j. So I think most of you know that in such a case, if you were to act as the oracle that had to give all these informations, we need to do some partial sums or prefix sums. So then think about this, and then what do we really get when querying CI CJ? Leave you 2 minutes. That's actually just 1 minute. Okay, any ideas with regards to this? Thank you, anonymous hippo. So yeah, that's the value that we get. Um, okay, and then another question: what would happen if we were to query something like ch? No, ci minus one. No, ch to ci minus one. Then we'd get s of I minus one minus s of h. And if h would be zero in such a case, after we've done these two queries, what do we find? So we actually get s of I minus 1 minus 0. We know this value. And we also know the value of sj minus s of I minus 1. So in total, we actually know both s of j and s of I minus 1, which is very good. Okay. Um, what I'd really like to do now is seeing that there's basically this discrepancy between the fact that we are getting something that involves both j and I minus 1, but we label it as I and j, to instead name a matrix D as the ij equals C of I plus 1j. Yes. Thank you, anonymous manatee. That is the final solution. So what we observe is that basically what we are given here is like okay, let's assume that we actually get so we relabel as like this, and we actually get s when we query ij, we actually get s of j minus s of I, and we know that s0 is 0 out of the definition, uh, and we also know that if we determine the array S, we can determine the array V. Then let's just focus on trying to determine the array S. Then what do we want is basically to find a way such that we can have multiple such relations that, similar to this case, when added, they go back to S0. That is, we have Sj minus Si minus 1, S of I minus 1, and then S of I minus 1 minus S of H is another relation that we buy, and then so on and so forth, until we should be able to keep adding such relations until S of J gets back to 0. So naturally, we might notice that such a chain of events is a chain. And we think, oh, chains, paths in a graph. Maybe we should draw an edge between the two values that we can determine by the relations that we have. Uh, so that's very good. Uh, so then, what does that leave us with? If we were to draw an edge, and uh, we might assume that it has weight, not our, but ij. But let's ignore the part with the weight so far. Let's say that we've got some relations already. We want all the relations that we got to connect every element j to element 0, because then we can do a telescopic sum to deduce s of j. And only now we can say that this is actually clearly MST, because yeah, we need to buy the connections, but the connections have a cost. So actually, we need to care right now about the cost. So we need to buy the minimum set of uh, relations such that they will describe every single j in the relation to 0. It would connect every single j to 0. But furthermore, since every j is connected to 0, that means that every j is connected with each other. So we really want just a connected component. And obviously, if the connected component has a cycle, then we can just erase one of the edges on the cycle because the graph would remain connected. So really what we want is what is called in the business We want a spanning tree. And now I will introduce the three main algorithms that are ever going to be used in any problem. There is a Kruskal algorithm, which many of you might already know. There is a Prim's algorithm, which you might know, but I pray you never get to use it. Uh, and there's Borufkal's algorithm, and there might be more, but I don't know them, unfortunately. Uh, these are the three main algorithms that are ever used in any uh, task with minimum spanning tree. I'll start off with Prim's algorithm, although I've listed it as the second one because I think it's the easiest one to prove, sort of. Prim's algorithm says the following: consider a random root for the final spanning tree. Uh, no, the minimum spanning tree. Okay, let me be clear about the thing. So the thing is that when we query ci of I, we are actually querying. So um, yeah, we add an edge between j and I minus one with weight ci of cj because we actually get a relation between s of I minus one and j, not something related to I. So for that reason, ci of I is not a special case. This is an older question, but I didn't get to see. Okay. Prim's algorithm says the following: consider a random root for the final spanning tree because we know that if we have a tree, we can just arbitrarily assume there's a root. Then, what would a minimum spanning tree right now look like? Then, consider all the edges adjacent to root. If the minimum incident incident means adjacent, adjacent, I actually don't think we can say edges adjacent, but whatever. Incident means that one of the endpoints is root. If the minimum incident edge of root is not going to be in the final solution, then that's false. We can just include it because obviously this is this follows from a trivial fact that if we have the root and there are multiple edges and this is the minimum one, but by the end we just choose these edges and we have like some tree that grows out of them, for example, then in such a case, like we can just say, okay, what would happen if we add this edge? Then there will be a cycle, and out of the cycle, we can erase the maximum cost edge because we'll keep the graph connected, and it will still be a spanning tree. And because we know this is the minimum, the value of this edge is less than the value of this edge, we know that after including this and erasing the maximum cost on the edge, this will still be in the solution. So what we've done is we optimize the solution, but more importantly, we optimize the solution that we assumed was already optimal. So then, trivially, uh, we will include the minimum incident edge. We now have a component of two nodes. Add then the minimum incident edge to either of them. And continuing to do this, we can just increment uh, the spanning tree one by one. We start with our root, we take the minimum incident edge, then we look what is the minimum incident edge to both of these nodes. We see that it's this node. Then we look again what is the minimum incident edge to any one of them. We see that it's this node, and so on. And we keep increasing the tree one by one. And because at every single point when we have this connected component, we can assume that we can just compress it to a single node and we are back to the initial solution. We know that the greedy strategy to keep adding the minimum incident edge will always form a valid argument. So we can still, every single time we expand our component, we can still always just add the minimum incident edge. Is that clear? There are two complexities that this algorithm can take. There is O of, what is it? I think maybe m log m, where m is the number of edges. Actually, let's just call it E instead. Or of v squared, where v is the number of vertices. This comes from two main approaches. We can either keep a priority queue with the with all the incident edges in the graph, and every single time when we want to extend our component, we take the minimum one and check whether we can include it, and if not, and so on. And we can do all of these operations with priority queue, or and this is where it shines against many of the other algorithms. We can keep a priority queue in Oven. What that means is updates would take Oven, but queries would take Oven. But since we will only do, no, updates would take O1, but queries would take O1. But since we will only do O1 queries, okay, I hope it works now. What is the meaning of update? Updates to the structure. I'll explain a bit more clearly right now. So, uh, normally, I hope for most of you it's clear what I mean by like right here that we keep a priority queue on all the incident edges. That is, we start with the initial node, as I said. We add in the priority queue all the incident edges. Then we take the minimum one. Then we unite those two nodes. Then when we consider the newly added node, we add all of its incident edges to the priority queue. And then again we take the minimum one, and then we get a third node. And then we insert more edges, and then we get a fourth node, and so on. And this will be a priority queue, a heap. But a priority queue in such a case can be implemented worse in like O of one update, but query in O of n. But that will be beneficial to us because we'll only do few queries. That is, consider for uh, consider an array where we keep on position I the minimum cost to add node number I to the component. Then, for example, when we start with the root, we notice all of its neighbors, so like v1, v2, v3, v4. And each of these has a cost to be included. Then, on their corresponding positions, we update with these values. We say that now we know that for v1 we can uh, add it to the component with w1 cost. For v2 we can add it with w2 cost. For v3 we can add it with w3 cost, and for v4 we can add it with w4 cost. And then when we want to consider what is the best node to include, we just scan this entire array and check for the minimum value. And let's say it's v2. V2 is the minimum value. Then v2 is also added to the it's added to the component. Then we check what the edges v2 would have. So maybe it has an edge to v3 with cost a1 and some other node with cost a2. Then we update those corresponding entries with the minimum of the new value and the old value. And then again, we scan the array to check what is the minimum node to include. What is the node with the minimum cost that we'd like to include? And albeit the queries take over time to find this new node to include, we will only add n nodes to the structure. So although every query will take us O of n time, we will only do O of n such queries. So then final complexity is O of n squared. The important thing is that there is no log. Whereas here, if the graph was really dense, that means E is very close to V squared, then V squared log V squared is kind of bad. Is that clear? Good. Initially, this task, I think when it was set in the original contest, you were supposed to, like, the only way to get 100 was to write Prim's algorithm. I'm not sure if this is still reflected on the online judge. But yeah, it's good to know sometimes that Prim's algorithm solves, and really you should only use Prim's algorithm, I think, in such a context where the graph is really dense. I think even Wikipedia states that it's the only use case. Okay. Maybe more famously, there is Kruskal's algorithm, which it's I think maybe many of you know it, uh, but it's based on a similar principle. Actually, all of them are based on the principle that the minimum edge at any time is a great edge to include. What does Kruskal want from us is to consider not an arbitrary root, but the minimum edge in the entire graph. Clearly, this edge will have to belong in the final spanning tree. For the same reasons that the minimum incident edge of any node would have to belong to the final spanning tree, the final minimum spanning tree. Wait, I think I never actually formally defined what a minimum spanning tree is. It was this actually, minimum spanning tree is a tree where the sum of the weights of the edges included is minimum among all the possible spanning trees of the given graph. Yeah, sorry. Uh, should I cover? Are there any problems? Yeah. The only time, yeah, the only use case of prim is when E is really big, and neither of these work when the number of edges is really big. But prim might work in such a case. And actually, I might be misremembering, but I think like at one point I solved a problem um, for which thinking about the way prim would work was better than Kruskal or Boruvka, but I unfortunately can't actually name it. Like the final solution was much clearer when you considered building what it was implied to be a minimum spanning tree by Prim's algorithm, because the problem structure allowed you to do Prim's queries better than Kruskal queries or Boruvka queries. Um, so it's just good to know, but you might never use it in your entire life. Okay. Kruskal's algorithm is based on the similar principle that we should include a minimum edge in the graph, because if we don't, then we can optimize the graph by adding the minimum edge, um, and then looking at the cycle, and we know that we can erase any other edge on the cycle, and we will optimize the final solution. So clearly, we should add the minimum edge. Then the second minimum edge should be in the graph, because the only time when this wouldn't happen is if the following were true. Uh, if we were to include this new edge, then in the consider the optimal solution first. Always consider the optimal solution and whether you can make it better. This is the basis of any greedy proof. So consider the second minimum edge. Then the only time when it would be bad is if in the optimal solution we know that after we include it, uh, there will be a cycle formed, and we know that in any cycle we can optimize the solution by erasing the maximum edge. But the second minimum edge can't really be the maximum edge, because there's maybe like the minimum edge, then there is this second minimum edge, but to form a non-degenerate cycle you need three edges. So there will be this third edge that will be greater than both the first and the second minimum edge. So clearly we should be able to include both, also the second minimum edge. then we can add the third minimum edge in the graph, but only under the same circumstances as before. Because if we need to know that if in the optimal solution we add this third minimum edge, it does not form a cycle. And now it might actually form a cycle because we have actually two edges that we know will belong to the optimal solution. So the only time when the third minimum edge would not belong to the optimal solution is if it would form with any of the edges that belong to the optimal solution. If it would form a cycle with any of the previously mentioned edges that belong to the optimal solution. That is, we do not need to consider what edges we might include later, because if this would form a cycle with them, then clearly we can erase one of these and this will still belong in the solution. We can still augment the solution to have this, but not whatever comes later. But if we can form a cycle with the edges that we know belong to the optimal solution, which have a lesser value than it, then in such a case, we should not include it. And we know what edges that belong to the optimal solution are because they are all of these that we've added before. If uh, we want to add an edge by iterating from the smallest to the greatest loss, if it would, yes, we can check with DSU. If it would form a cycle, then do not include it. And we can check this with DSU. And the time complexity is like O of DSU, which is, I always like to say it's O of n, but it's currently just doing path compression is O of n log n, and you have to do both path compression and the area trick. Uh, yeah, it's O of DSU, which is this entire step, but there's a hidden step that it's barely mentioned, and it's that of sorting the edges. Whatever complexity that will have, in general, it's E times log E. But if the costs are small, for example, we can do counting sort. Wait, am I still? No, I'm not. Can you hear me? Okay, yeah. Okay, so is Kruskal's algorithm clear? And the final one that I don't think, like, I at least heard of it very late in my life is Borufka's algorithm, which you will never actually use to solve a minimum spanning tree problem, but every time that you can solve a minimum spanning tree problem. That is, in every single one of these cases, we can like very clearly say, we can very clearly point to what the edges are. most of the times we assume that getting an edge, we assume that either getting the list of all edges is possible, or that querying for the minimum one can be done very fast. But Boruvka is good because it helps to parallelize what in the other two it might be very hard to do so. And it's of consider every node in the graph and its minimum incident edge. Then add all these edges to the final spanning tree. Then consider all the newly formed components and their minimum incident edges to other connected components. And add those edges to the final spanning tree. That's all. You might notice that this algorithm is maybe quite similar to Prim's algorithm, because here also we had a component, we kept adding one node one by one, but the difference between and what Prim did much better than Boruvka was that we did not consider every node, because this is an implicit of n span. Although, like, this is just DSU operations, something. We have O of n scans times the number of times we have to repeat this algorithm until we have just one single connected component. But it turns out, fortunately, that the number of times we need to apply this algorithm, this step of getting the minimum incident edge for every single component and then adding it to the spanning tree is this is very easily proven, and in many cases it's much less than of n log n, much less than of log n, because not really. Because every single time that so what we actually define here is a functional graph. We define that we want to go from f of node to f of u if u v is the minimum incident edge. So we will define just this function. For every node, what is the neighbor to which we have the minimum incident edge? And we know that in such a case, we know that functional graphs are formed of like cycles and whatnot, and like little trees that go outside of this. And there are multiple such components. But what is the minimum size of such a component? Well, it's 2. Because the only time when it could be 1 is if f of v would point to itself. But v cannot be its minimum incident neighbor, because we can that just doesn't make any sense in a perspective of solving MST. So every single component would have size at least 2, which looks like this. When your best friend is also to your best friend, you're also his best friend or something. So the minimum incident edge goes to someone, and they also have the minimum incident edge towards you. But in many cases, it might turn out that it's like a bigger graph. And so really what happens is that the number of connected components that we had at the start was n, but then we compressed these to at least n over 2. And then this we also compress later on to n over 4, and then to n over 8, and so on. And how many times we can compress by dividing by 2? Well, log n times. Is Borufka's algorithm clear? So maybe, again, I don't think you are actually given a explicit if you would use Borufka's algorithm. We'll go into use cases, but this is the algorithm would look like. If edge is not connecting to the same component in the SU. Edge equal to edge. Connect the SU with edge. Yeah, this is the algorithm. Are there any questions? Except for applications. We'll get to applications later. Okay. In such a case, I think the next task that we could cover is the following. Still from the given homework. But what is the time complexity of it? So it really depends on what it looks like, but the most important thing out of Borufka's algorithm is that this step, like ignore the step where we need to find the minimum edge to each of the nodes, because you'll see in such cases there's actually like a much bigger data structure to handle these queries. But if we actually had like a graph, then this step would take O of E time. So so the number of edges, because we're iterating through every edge essentially here. And then this step, the number of times we repeat this is O of log n, because after every single step that we do here, we will connect at least, so each node will be connected to another node basically. So by the end, in the worst case, we will pair nodes two with two, basically. So nodes, let's say A2, A3, A4, subcodes that we have. After one step, it might turn out the case that we find that the minimum edge of A1 leads to A2, and also the minimum edge of A2 leads to A1. Then A3 with A8, then A4 with A6, and A5 is to A7, but A7's minimum edge is to A8, and uh, A8's minimum edge is also to 7. In such a case, after we compress all of these components, you notice that we will have 4 components. Because every single component that we will compress will have a size of at least 2. So from 9 nodes, we'll go to uh, at most n over 2, 9 over 2 more components. And then connecting these components between each other will lead to, by the end, after this, we will have at most 4 over 2 components, which is 2. And then after connecting those 2 components together, we'll have one more time, one single component. So because every single time we are halving the number of connected components that we have, the times we have to repeat this algorithm is O of log n. Yeah, so essentially whenever you are given an explicit graph, I recommend Kruscals because it's very easy to write. But it is very good to know all of these other approaches because they might appear suddenly problems, such as this one. Wait, apparently Fijaj is done. This task asks us to find the MST. Yeah, it just literally says both in the title and the problem, calculate the weight of the minimum spanning tree. But there is an issue. The graph they gave us has n squared edges, but n is 2 times 10 to the 5. So that means there are like 10 to the 10 edges. So I'm not saying anything, but yeah, it's a harder problem to approach with standard uh, yeah, with standard approaches. I guess I should leave some time, but I don't think it will be very necessary. Till let's say 16, maybe even earlier. Uh, okay. If any of you have an idea that they want to discuss, and for this reason, write in the and yeah, if you have any idea that you'd want to discuss, please write a message and I'll get to it. But yeah.
Whoa. Why does it matter who they are? They're an anonymous dinosaur or something. Okay, so yes, the better solution. I don't know who said it. I think it was the dinosaur. I didn't see. I think it was the dinosaur. Who was it? Iguana or dinosaur? Who won? I'm not sure. Okay, but yes, the better solution is to use tree. I'm not sure how you pronounce this. I know it's tree. Like in English, it's supposed to be tree from retrieval, but uh, it sounds weird to say a tree because that's obviously, and I don't want to say try because that's also another word in English and it sounds worse than tree. So I'll say this is a tree. So we can use tree and boruvka. And to go over very quickly on how that would work, it's the following. So assume we have all the connected components placed on a line. These are all the nodes of the first connected component. These are all the nodes of the second connected component. During the then what do we want? We want asks us to find for each of these connected components the minimum edge towards any of the other connected components. So, example for C1, uh, we need to find a maximum of A1 XOR A uh, C1 times A from C1 is an index from C1 and A is strictly speaking, just for C1, we can solve this problem by implementing the tree. So yeah, sorry. It is in max. It's the same thing, min and max. Sorry. So we want a minimum edge from C1 to any of these. So we can just build a tree on all of these values, of all the values of all the nodes outside the connected component. And then for each of the nodes, we can query this with a tree. I won't get into how you actually do that, but if you actually have the tree written, it's just a matter of DFS within the tree. Like here, every time you try to go towards the thing that would still keep the XOR on that level 0. And if not, if you don't have any nodes in that direction, you obviously choose to have 1. Okay, good. The issue is that if you were to build a tree for all of the nodes outside every single connected component, clearly, or actually no, it's not an issue. Yeah, that's what we should actually do. So normally I'm very influenced by another problem that I've given you with this that instead has to use CHT to do that, and from CHT you can't actually delete. But in such a case, yeah, normally what we can do is just keep a tree on all of the those nodes, and when we want to adapt the solution to find for C2, which is the minimum and the argument of the minimum of this expression, we can insert in the tree all of these nodes, and we can just erase from the tree all of the nodes of the second connected component. And when we do this, that's like we can actually perform these operations, erase and insert. And then when we get to C2, we'll have in the tree all of the connected components and all the nodes within them, except for those in C2. So then we can start querying same as before. And for C3, we can do that as well. But in situations when we when erasure from the data structure is not trivial, one can employ the following approach. We can iterate from right to left a tree, and every time we get to a new connected component, we can query basically the minimum on the suffix, the minimum XOR on the suffix of connected components. And then after that, we include the connected component into the data structure, so one by one. When we get to C3, we'll have all of these in the data structure. When we get to C2, we'll have all of these in the data structure, and so on. And then we have the minimum edge towards the right. And then we can similarly go from left to right to query the minimum edge towards the left. And then we take the minimum of either. This is when we can't actually delete. But in such a case, we can delete and it looks much clearer that way. So at every step to get the minimum edges, we'll have of and log. Because for every single node, we'll have a query and log to find the minimum edge. And also because Borufka has log n, we have to iterate Borufka a number of log n times. The final complexity will be of n times log squared. Well, actually, it's like log x. Okay, good. Now, since everyone solved the 2300 rated problem, let's solve a 3100 rated problem. The next task that we will discuss is this one. Actually, I forgot what it said. It's solution vaguely to my disappointment. Oh God. Okay, what about problem? Yeah, so I think the statement is quite clear and direct. We are given a graph. We find the cost of f from A to B to be equal to maximum maximum edge on the path or given yeah, this problem is so bad for my given the following queries, insert all I from L bar in S, erase all I from L from S. determine uh, the value of varies type uh, for given u, determine v such that cost uv is maximum and v is index. Uh, for the test, I think we can wait until 1 minute as well, maybe less, I'm not sure. Yeah. Okay, so I think we should start discussing the problem. Uh, I said initially that the problem is very bad because you see by the end it's just an amalgamation of multiple tricks, one by one. Uh, so that really just makes the problem good for I don't know why it's given in a code for system. Um, so the one of the issues is that maybe we don't know how to calculate this value. Like like let's say just one single query, one single time, or like I, I'm uh, I'm giving you u, I'm giving you v. Please determine cost uv. Because the thing is that we can't just return the maximum edge. We are not allowed because we need to construct a simple path. So that is very important. But regardless, let's consider what the maximum edge is in the graph. Okay. Hmm. Wait, I might have forgotten the solution to the problem for some reason. Uh, am I stupid? Wait, this is a weird thing because I used in the solution something that I shouldn't have used. I think the code that finally got the points, and I'm quite confused at that. Uh, Wait. Okay, so what I was about to say normally is that we build the MST and we notice that at least for the minimum spanning tree, the minimum possible cost from one node to another is the maximum on the path in the minimum spanning tree. And this is an important property that holds in general, but, and I should explain it, but for some reason I build a minimum spanning tree and I say that this is the maximum. I should have misread the statement because I do have accepted. But like for some reason I build the minimum spanning tree, although for instance, if we take the maximum edge, the edge with the maximum cost, normally if we erase it, or is the given graph, oh, the given graph is a tree. Okay, sorry. I assumed that the graph was not a tree, but it is a tree, which is okay, even worse, so much worse. Okay, so that makes the problem even weirder because I'm asking you to build a minimum spanning tree, although the problem already gives you a tree. So yeah, but okay, so consider the maximum edge in the given tree. So this has the maximum cost. Okay, then what can we say? If at any point in time there is both a node on the left side and on the right side of this edge, so on the left, no, that's the right, sorry. So on the left and on the right side, there are both two grocery stores open when we do the query, then regardless of where the query node will be, whether it's left or right, we can traverse this maximum edge to get to the other side, all while passing through the maximum cost, the maximum edge. So maybe this reminds you a bit, and I hope it does, of Cartesian trees. And it turns out they are very related by the end. Because we have this maximum thing, and there is the left side, there's the right side, and like right now I've drawn this to be like on top with greater priority. And then I say something, oh, if I come from the left side to the right side, I pass through the greatest thing ever, the biggest thing ever. So yeah, it's I think it's important to say right now that maybe this should remind you of Cartesian trees. And to follow up on that intuition, let's say this is the maximum. Now let's look at the maximum within only one of these subtrees right now. So let's consider the next maximum edge, because this was easy. However, this isn't really easy because the maximum edge will be like some random thing. The maximum edge in one of the subtrees will be like some random thing over here, and it really solves the problem for like everything above and everything below. So if there is a node for query here and an update and an open store here, or vice versa, then we can traverse this edge. But really what we can just say is that we are not interested in how this subtree behaves after we root it in either one of these nodes, because each of these subtrees is now an independent problem. So just as I said previously in the Cartesian tree, that if we solve the left side and the right side, we take the maximum and draw an edge between them. Let's just do that. Let's now solve the left side and the right side. But what would happen if we solve the right side with disregard to the rest of the subtree? So like if we just just consider everything, what happens in this subtree. Then we have this edge, and we decide that we should put it on top, basically, just so it so we can look at it better. So this is second maximum edge, and there is like a left subtree, which is everything below this, and there is a right subtree, which is everything that's not below the edge, basically. And similarly, if there are two nodes over here, then for any query of any node that is within this subtree, so if the node starts in this subtree, if we have this both an open store here and an open store here, the answer to the query will be this second maximum, well, the second maximum edge in this case. But if it isn't, then there are some other cases as well. Like, for example, let's say that there are no two open stores. There isn't an open store in the left side, and the only open store is in the same side where we start. Then we will not be able to take the maximum edge because there is like maybe no store on the left side, so we cannot cross it. And there is also like no way to cross this edge because we are both stuck on the same side of both edges with respect to what stores are open. So we should continue to split down by this process. So we have a tree and we build a Cartesian tree, Cartesian-like tree. Such that we start with the given tree. So it looks like this maybe. We take the maximum edge. Can I do a little thing and copy this? Yes, I can. We take the maximum edge and then root the entire tree with respect to this edge. So we put it like on top. We now have the left subtree and the right subtree. Then construct a Cartesian tree on the left and on the right. We now have a Cartesian tree of the left, a Cartesian tree of the right, and we will draw an edge between these two with cost equal to W. Like there will be a node here, we'll give it value W, and it will be the root of the new tree. Is it clear where I'm going with this? Like what I'm actually building? The most important thing before I ask whether it's clear actually is that by the end, we'll have a structure that behaves exactly like the Cartesian tree. But more importantly, what I mean by that is that the maximum on the the maximum on the path in the first tree is the LCA in the second tree. So for instance, what happened here is like, let's assume that we have two nodes either on the left or either on the right. One on the left and one on the right. Then when we take the LCA in this new Cartesian-like tree, the LCA will be this edge, this node that corresponds to this edge. So then the LCA will say that we have an edge that the maximum cost will be W. Whereas maybe we could have solved by binary lifting or whatever. In the original tree, we could have just taken the path and take the maximum edge on it with like binary lifting or something, and we'd still have the answer as we'd still get the same answer. We'd still get the same maximum edge. But if the two nodes are on the either left or on the same side, then by recursive by induction, the LCA of them in either of these two cases will still be the maximum on the path. And then let's build a Cartesian function in the Cartesian let's say of any two nodes corresponds to the maximum edge. And so after we create a Cartesian-like tree for L and for R to keep recursion going and keep the inductive process true, we will create a new Cartesian like tree for this entire tree where we actually have this edge as the having a root associated value equal to W and two edges towards the roots of Cartesian tree of L and Cartesian like tree of R. Is this here? All I did so far was to make the thing that we initially had, which was a bit awkward because we had to calculate the maximum cost on the path from some given node to some set of nodes, and I rephrased it to have instead of the maximum value from a node to a set of nodes, we now have a construction where we have to find the we now have actually just right here. We now have to find, instead of max from U to B on the path, to find the uppermost, let's say, possible from a given U to some V in the set. And I think that finding whatever uppermost means, uppermost would mean, it's still much better to calculate like some LCA with V with regards to a set S rather than the maximum from U to V on some path, blah, blah, blah. Mostly because actually, essentially, we will find that this LCA that we want to find is just the LCA of V and all of the nodes in S. which is very easy to do, in fact, but we'll get to that later. Uh, getting harder and harder. I assume not my voice, but what I'm trying to explain. Okay, so how did we start? Uh, so the problem asks us to we are given a set S that keeps on modifying randomly, and very hardly so, because we have to insert like a linear number of things in S and a linear number of things in S. So we assume that this should have to be dealt with some segment tree or something like that. But essentially what the hardest thing is that even if someone gives us the set S and all the time to pre-compute stuff in it, the issue is that we have to determine for a given U the maximum cost from U to something in S, where cost U is the maximum edge on the path. So like it gives us a tree, and it tells us here are some nodes, and I'm giving you a node somewhere random, but you have to find so we have like maybe a lot of time to pre-compute things until we get the query. But when we get the query, we should do it as fast as possible. We should be able to do it as fast as possible. But like, if you were to solve the problem of find the maximum edge, find the maximum cost of U to any V in this good set S, then this at face value is very hard to calculate, because to calculate the cost you have to do like a binary lifting. And if we keep this rigid structure of the cost can only be calculated using binary lifting on the path from the two nodes that we have to calculate between, then we will not really get anywhere, because we still have to do the binary lifting from the given node at the query with every single node in the set S. And we really want, although we can pre-compute in much ever time we want to be able to query things faster. And so we notice that if we take the maximum edge in the tree, it's good to ask whether we can actually use it. Instead of doing like binary lifting every single time for every single node, let's like instead just consider the maximum edge, maximum value edge in the entire tree. When can we use it? We can use it if on one of the sides we have an open store, and on the other side we have the node given at query. Is that clear? %60. So so we want to find a new way to calculate this maximum. So we just abandon the entire notion of maybe binary lifting or whatever the cost means and like aggregate on path. So we just erase it. Let's not even think about it. We know that the final value that will be the answer will obviously be equal to the value of a single edge. Like there will be a single edge that will actually trigger the cost to be exactly that. And if we take the maximum on the path, maximum on some path, and this path contains the maximum edge, if we know that the maximum edge belongs to the path, we can just basically ignore the rest of the path, because we know that 100% the cost of the path will be that maximum edge. Because again, not the maximum meteor, blah, 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 the maximum cost on the path. So let's look at the maximum edge. If we know that in the set that we are given at query, so imagine we are given the set and we have to query as fast as possible, but we can pre-compute, like there are no updates. There are some initial updates, but after all the updates, there are only queries. There are no more updates. So first updates, then queries. Then look at where the maximum is. If the query node is on one side of the edge, like in one of the subtrees, it splits, and we have an open store on the other side, then we can traverse it. We can traverse this edge. There will be a path. But if this were not the maximum, and instead the maximum edge would be somewhere around, like let's say over here. This is the maximum edge. Then there is no path that passes through it and goes to an open store. Because to start here and go all the way over here, we'd have to continue somewhere in this subtree, but there is nothing in this subtree. It's barely even a subtree. So that means it's useless. So because we noticed this sort of left thing and right thing, I want to remind you what we did in some previous lesson with the Cartesian tree. So let's take this maximum edge. There will be a left subtree and a right subtree. And given that, similarly, as I've said in the Cartesian tree, if we were to solve the left subtree, any query in the left subtree, however we want, and any query in the right subtree, whatever it would be, then how do we solve queries where one node starts in the left and one node starts in the right? Well, we can build a tree-like structure where the solution for the left side is a tree, then this max edge is the new root, and the solution to the right side is also a tree, which is connected to the new root. Then any query that starts in the left and in the right, and ends in the right, will have the LCA equal to this maximum edge. It's just the same thing, the same principle as with Cartesian trees, only that it's a Cartesian tree on a tree, which is a bit weird. I got the 60% of full idea. Is the idea more clear now? I mean, I don't expect you to be able to right now, because I haven't actually said how to compute this final tree. What is the tree that I will construct clear? Maybe I should make an example with the So let's construct the tree for this instance. We will put the edge of 5 on top. Okay, great. Okay, then I will have to solve the left side and the right side. Let's solve the left side, which is just now a tree that looks like this. 1, 2. Then I'll take the maximum edge and solve it further. And what it would look like is like this. It would be this second maximum edge. Then the next edge equal to with value 1, and on the left side there will be just node number 1. Okay, let's label the nodes 3, 4, 5, 6. On the left side, on this single subtree, there will only be node number 1, and on the right subtree there will only be node number 2. Then for this entire subtree, we have the subtree. Wait, sorry, no, it's not true. We have the solution for this subtree and also the solution for this single node. So we will connect the solutions for 1, 3, and for 2 by means of the edge with 2. So in this case, look, the LCA between 3 and 2 will be this edge node, this node of value 2, which corresponds to the maximum on the path from 2 to 3. Also between 1 and 2, the LCA will be equal to this 2. And similarly for the right side, we will by the end have this structure. So the leaves will be every single node that we have in the tree, and the intermediate nodes will correspond to some edges in the tree. So then look, the LCA between 3 and 4 in this case will be clearly 5. This also corresponds to the maximum on the path from 3 to 4. Between 1 and 6 as well, the LCA will be equal to 5. So now, instead of having to calculate maximum of cost on path from a given u to some value v with v belongs to some set, we have to calculate maximum of LCA of u with some value v, where v is in the set. Because of the way that we restructure the edges in the tree. And also because we can see that the LCAs, the more we advance towards the root, they increase. Then we really just want the cost of the LCA between U and the entire set S. And to calculate the LCA between a node U and the set S is much more easy right now. Can we agree on that? Is it a bit more closer to like 80% now? Let's say 80%. No? clearer now? We are actually constructing. So I will be constructing an auxiliary tree, a completely new tree, which preserves the structure of the initial one, while adding the following property. The LCA between any two nodes, leaves, which actually correspond to nodes right now, is instead the LCA between, okay, so the LCA between any two nodes, which correspond to, between any two leaves, which correspond to nodes on the initial tree, will be the edge that is, that has the maximum cost between the two of them. And we do this with a divide and conquer like approach. Okay, so assuming this construction exists, then trees are now only given set S, determine let's say of U for tree of U, and let's say of U and S, because this will be the highest edge you can reach by going through a node U and later on through a node S. Because if the if every single node is completely included in one of these subtrees, which correspond to some edge, then it means that for every single greater edge, there will be nothing on the right side, such that we can start on this left side that we are actually in, and then end up in that right side, and in the meantime passing through that greater edge. So then the LCA corresponds to the maximum edge, where we have something on the left side and something else on the right side. So then in such a case, we can actually traverse that edge. Okay. This is much easier, and it's we can calculate the LCA of a given set by the updates that they give us, by calculating the pre-order of each node, and by the end, the LCA of the entire set, because we can stick this in like the LCA of this entire set will actually correspond to the LCA between the node with the minimum pre-order that is active and the one with the maximum pre-order that is also active. And then this these updates can be held in a subtree, in a segment tree, where we keep the active node with the maximum toggled value and the maximum pre-order value that is active, and the maximum the minimum pre-order value that is also active. And this is just lazy update to turn on or turn off some subtrees in the segment tree. And there is one more question left to be answered, and I don't think I actually have time to clarify everything, unfortunately. Is how do we calculate this Asian like tree of initial? Well, it turns out that this is what we call a Pascal reconstruction. Maybe in your spare time you'd have more time to read about this. But essentially what this means is that, let's say that we were actually applying the MST algorithm to this very same tree. Then when we look at the smallest edge, like in this case it's the edge between 1 and 3, we can, MST asks us to unite it. And we can just do that. We can unite them, and when we do, we will add a node between them to say that if we want to traverse 1 to 3, then given especially that they are adjacent edges, the maximum cost on their path will have to be clearly 1. There, there is no better solution, especially because of the fact that they are adjacent. And then when we take the next edge from 2, 3, by similar reasoning, there is no better solution for anything in this subtree that is already connected by edges of cost less than 2, and anything on the other side, which is also connected by edges of cost less than 2. And so at the time when we do the Kruskal algorithm, we notice that we will merge one and the connected component of 1 and 3 with the node 2, but we will actually connect the structure of 1 and 3, which involves higher root of cost 1, to a higher root of cost 2, and the simple node of label 2. And we do similarly this for the left subtree, where we unite 4 and 5, and we say there will be no better solution to go from 4 to 5 with a greater cost than 3. Then we unite 4 and 5 with 6 and say there will be no better way to get a cost from 4 to 6 than with cost 4. And then we will unite both this 1 to 3 subtree with this 4 to 5 subtree by the edge of 5 in the root. And we will say there will be no better way to traverse from either of these to either one of these on the left side, on either side of the edge, than by the edge of cost 5. This will be the maximum edge that we will be able to traverse at any time. Not too much contribution of spanning tree. Yeah and no. I mean, essentially although the problem is a tree, and I've asked you, it's a bit stupid to say indeed that this problem is a spanning tree problem because it starts with a tree. There is no spanning tree of a tree. The spanning tree of a tree is just a tree. But in many other cases with other types of graphs, the Kruskal reconstruction tree calculates the following. So if we were to apply this Kruskal reconstruction tree construction, where we keep adding, instead of uniting things in the DSU simply, we add a node between the two subtrees that we are uniting at every time during Kruskal. If we were to do this on a graph, it will actually represent the LCA of the node will represent the following. The minimum cost will go from U to V if the cost of a path is the maximum on the path. And for this reason, it's especially useful because maybe sometimes, for example, if the cost of the path would be the sum of the edges on the path, like how it would look like in a Dijkstra algorithm, then the problems where you have to calculate multiple such costs are impossible. But in problems where you are instead, for no reason at all, you are given a graph and you are asked to calculate many maximum on paths, and have a better order of doing so, then again, ordering these in an LCA-like structure, as given by the Kruskal reconstruction tree, is especially useful. So fortunately, that's no problem. That's it, and that covers most what I intended to do today. Sorry for the explanation. I hope you sort of understood something, and I encourage you to implement. I think the editorial should cover things in more detail, especially on this side, where we have you have to calculate the ELC of U with S. Even though that we have to calculate the ELC, maybe it's not clear how to calculate the ELC of the entire set and how to do the updates. But other than that, this is it. Are there any questions before I go? Or do you all want to go home? And sorry for keeping you 15 minutes over the schedule. If not, then that was the lesson for today. I will add more problems in the homework, which is already available on Discord, and obviously I encourage you to do the homework, and see you tomorrow.